We can start with our last presentation for today. It is once again a space-related topic, also relating to spacecraft and all those fantastic things. Carlos Fernandez has come from Spain, and he has developed software for software-defined global navigation systems receivers. Please welcome on the stage Dr. Carlos Fernandez.
Thank you. So, first of all, I want to thank the organization for inviting me to this awesome event, and also thank the public for being here in this last presentation of today. Today we will talk about global navigation satellite system receivers defined by software, and more specifically in open source software. Hello? Yeah.
Okay.
I think it's working.
Stick this to the side. Okay.
Okay, so let's start. This is the overview of the presentation. First, I will introduce briefly the topic of navigation. Then we enter into the details of what a software receiver for global navigation satellite systems is. And then we'll talk about different possibilities that we have explored with this kind of technology, and finally draw some conclusions. First, we can talk about the art of navigation. We talk about navigation of the art of finding the way from one place to another. It comes from Latin navis, which means ship, and gear, which means to move or to direct. But today, this encompasses the guidance of travel on land, in the air, and the inner outer space. We will see that there have been a incredible evolution in technology related to how humans navigate. We can talk on the topic of navigation on different points of view. One could be the biological navigation. I just made up that term. I don't know if formally it's called like that, but it refers on how animals and how humans get from one point to the other. There are extreme examples of that. For instance, a taxi driver in a big city like London that have to bear in his mind all the map of the city and how to reach each point from another. Professor John Keefe got a Nobel Prize for studying that, so it's not a joke. Then we could talk about maps, which won't be covered here, but a lot of evolution in geodesy and surveying and geographic information systems and so on, also in route recommendation systems. But today here we will talk about positioning, about the knowing where you are, anywhere at any time. If you talk about indoor positioning, you can rely on different wireless communication systems or inertial measurement unit for doing that. But in outdoor positioning, GNSS, which Global Navigation Satellite Systems, are the technology of choice for that. You can have a commercial chip device, a chip receiver, which can give you a position with some meters of error, tens of meters, let's say. Then you have professional GNSS receivers, which are able to give your position with a precision of centimeters. And then there are free and open source software-defined radio for that, which is exactly the topic of this talk today. We won't talk about interplanetary navigation, which could make maybe with pulsars, which are very stable clocks in the sky. But we will remain on Earth in this presentation. There is a fundamental problem in navigation. The latitude is quite easy to compute, starting from the sun, if you see the sun actually. But longitude is a little bit more complicated, and you really need a very stable clock for that. You need a time reference for knowing if you are on the east or the west, which is the longitude. So there have been a lot of evolution during history about the technology using for that. You can see here the magnetic compass that made the Chinese in the ancient times, the astrolabe. Maybe you can see the first first watch there, which was made near here in Nuremberg. And then we have the sextant and the clocks made by John Harrison, which was the winner of the longitude prize, the guy who really got the technology for ships, for navigation at the sea. Because at those times we had sand clocks, we have pendulum clocks that doesn't work in a ship. So we need mechanical clocks, and this is the guy who made it. So there is also an evolution in metrology and in geodesy. For instance, here you have the formal definitions for what is 1 second or what is 1 meter. Without context, they seem quite crazy or arbitrary. We have learned about the shape of the Earth, which is not spherical, which is more like a potato. And finally, today, the technology has allowed to put those clocks in the sky. This is basically a satellite for navigation. Very good clocks, actually, cesium and rubidium based, highly stable, and they are continually monitored by a ground control segment. And today we have more than 100 satellites that are broadcasting these kind of signals, open service signals, to different in many different frequency bands. So this is really a playground for software-defined radio. Here you have the list of open service signals that you have today. GPS, we have 24 satellites. They are broadcasting open service signals in 3 different bands. They called L1 is the one that you probably have in your own smartphone. But we have more systems. We have the Russian GLONASS system, also with 24 satellites, different bands. Galileo, which is the European one. Currently, I think there are 22 satellites in the sky, also broadcasting signals in 3 different bands, and the Chinese BeiDou, which they have also three bands in which they are transmitting. So a lot of signals to play with. Little bit of theory, just a little bit. Any kind of GNSS signal can be expressed with this equation that I'm writing here, in which you have a pseudo-random code, which is, do you see my, yeah. This is a sequence of plus and minus ones that are moving very quickly. And this is modulating a message which is here. And in this message, we have information about where the satellites are. These messages convey the Keplerian parameters, in which you can make use of them to know exactly where the satellite is in that moment, so you can compute your own position. So we can write particularizations for all kind of open service signals based on this signal model. So there is a lot to do for aficionados to software radio, because you have a lot of signals and satellites to play with. So let's see what we can do with them. So here's basically how a GNSS receiver works. They are getting signals from different satellites. And you need to solve a system of equations in which you will have at least 4 unknowns, 3 for your position and 1 for the time. So these 4 unknowns mean that you need to see at the same time at least 4 satellites in order to compute your own position. So let's talk a little bit about what is the mathematical model for any kind of software radio. And this is based on an old theory made by Kant, which talk about a network of processes. And this mathematician established the fundamentals of how a network of processes can communicate together in order to execute a network process. And he also established that you can make a network of processes that at the end of the day will give you a deterministic output, which is really what you want. And also this is very important because each process can be executed in a different thread, so this is very important for multi-threading and for accelerating the processing on all this stuff in a computer. So these CAN models of process networks, they say that you must hold to K properties. One of it is non-termination. It is understood as an infinite running flow of processes without deadlocks. This is important. You don't want a network of processes that get caught in a loop. And they must be strictly bounded in the sense that the number of data elements buffered on a communication channel need to remain bounded for all possible execution overloads. So this means that any kind of software-defined radio can be expressed like a flow graph. Here you have the most basic one, in which we have one source, which is one node. There is another node in the middle that actually does the signal processing, and finally a sink, which is taking the results of the signal processing. This would be a very simple flow graph of how a software radio works. Each of these nodes, as implemented by GNU Radio, if you see the inside of those blocks, we can see something like that. There is an underlying runtime scheduler that is parceling out the work of the computer in different threads. You have an input buffer which you read samples from. You have a work method which actually does all the signal processing, and you write your output in an output memory buffer, which will be the input buffer of the next block. So this is how you chain blocks together in GNU Radio. So we developed a software for receiving this kind of signals. It's called GNSS LDR, not a big display of creativity in the name, but you can use it with several frequency frontends. You can work with in real time, working with a front end, or you can work in post-processing, just processing samples which are stored in a file. The software is written in C++, it's multi-platform, and is released under a free and open source software license, which is GPL version 3. So this is a generic flow graph for GNSS SDR, in which we have a signal source. Then we have a block which we call signal conditioner, which is about filtering and bringing the samples to baseband if they are not already there. And then we have any number of parallel channels that are all doing the same, each one for one satellite. And each one, what it does is just to do signal acquisition. That means knowing what satellite is actually in the sky. Then we have to do signal tracking. We need to track the evolution of the synchronization parameters of those signals. Then we need to demodulate the navigation message, which is that message that conveys the information that you can use for knowing where the satellites are. And then collecting all these measurements, you can form something that is called the observables, which are the basis for computing what is called PVT solution, which is position, velocity, and time solution. And there is an underlying scheduler that avoids these processing bottlenecks in the whole processing. Here you have the class hierarchy of GNSS SDR and its relation to GNU Radio. So we really inherit all the good things of GNU Radio in terms of how to define these processing blocks and how you can chain them together. And then we have a special block interface for GNSS SDR, in which we can have For instance, channel interface, acquisition interface, tracking interface, and so on. These are abstract interfaces that now that then we can populate with different kind of algorithms. So with the same flow graph, we can test many different algorithms. It's very easy to, if you come out with a new algorithm for signal detection, you can just plug it there, and you will see how it works in the whole receiver, which is quite nice. So this is the flow graph in more detail. Here we have the signal source that can gather samples from a front end or from files, the signal conditioner I was mentioning, then n parallel channels, the formation of observables, computation of the position, velocity, and time solution, and then outputs in many different standard formats. So this is the main flow graph for our software, and then each of these blue blocks are populated with different algorithms. For instance, we can do more complex thing. Maybe we want multi-system and multi-frequency receiver, so we can do that. So we can spend some signal conditioner for one band, and then several blocks, for instance, for GPS L1, other blocks for instance, Galileo E1, and then here the same thing for another frequency. For instance, here I put L5 with GPS L5 here and Galileo E5a here. So this would be the flow graph of a multi-system and multi-frequency receiver. The signal source, the first of the blocks, is an abstraction that wraps any kind of signal sources. So you can use popular radio frequency front ends, could be a USRP or HackRF, or well, many of different hardwares available. As long as you can write a new radio source for them, you can use it right away in this software. And then we can also read samples from different file formats. So we have a quite wide range of signal sources we can use. Then the next block is the signal conditioner. This is a hierarchical block which are formed by 3 inner blocks. The first one is the data type adapter, which adapts the number of bits of your samples to something that a computer can deal with. Then we have an impulse filter, just if you need it, if you want to filter a little bit more your signal. And then you have if you want to use it, there is a resampler for adapting your data rate to something more variable. Any of them can be bypassed. So this is an optional block just to condition your signal in case you need to. And then we have a number of parallel channels that encapsulates the blocks for signal acquisition, for signal tracking, and the modulation of the navigation message for each of the satellites you are seeing in that moment. So these are abstract interfaces that need to be populated with actual implementations of algorithms. And one nice thing here is the thread per block scheduler that we inherit from GNU Radio automatically manages these multitasking capabilities of modern multi-core processors. It really helps to accelerate the process and reach real time. So talking about signal acquisition, again, just a little bit of theory. Signal acquisition is something that can be posed as a detection theory problem, in which you have two hypotheses. The null hypothesis is that the satellite is not there, and the positive hypothesis that say that the satellite actually is there. So the solution to that statistical problem says that you need to maximize something that is called the cross-ambiguity function, which is nothing more than your input, which will be here, multiplied by the pseudo-random code that identifies each of the satellites with different time delays. And you also need to multiply by different Doppler shifts in order to get the one that is conveyed here. So you will have here two-dimensional space search, one in time delay and another one in frequency, and you need to detect the peak of that. You can see it graphically here. This would be the example of a positive detection of a satellite, in which you see here clearly a nice peak. And here something more in which you don't see this clear peak here, which everything is noise, and this is the case in which the satellite you are searching for is not present. So the acquisition block in GNSS DR, the role of this block is to detect satellites. And in case of positive acquisition, it should provide a rough estimation of time delay and Doppler frequency in order to fit the tracking loop and track the evolution of those parameters. So once you have this peak detected here, you will have an estimation of time delay and an estimation of Doppler shift that you can inject to the tracking loops. I want to mention a challenge here for real-time software-defined radios. You really need to work on to minimize the time you spend in the computation of this acquisition. So you take some samples from the flow graph of samples, you take some of them, you do the computation, and you inject them, but maybe the evolution of the parameters have moved. So you need to make this interval as shorter as possible in order to really catch the synchronization parameters. Then we come to signal tracking. In this case, it's not a problem of detection theory, it's a problem of estimation theory. Here we follow the maximum likelihood approach that says that you need to maximize the correlation function. The maximization of a correlation of any kind of function usually implies a derivative, because you want to get the cross in the zero of this derivative. And since we are working in digital systems, this derivative turns to be finite differences. And this is how this early, prom, and late DLL architectures arise. It's just doing finite differences in which you want to catch the peak of the correlation. And here, sorry. And here you have three correlators. One is a little bit before your estimation. There is the prompt correlator, which is actually your estimation of the peak, and there is a late correlation. And based on the differences on of these values, you can really track the correlation function and so the synchronization parameters. So this will be a diagram of what is a delay lock loop and what is a phase lock loop, to call it PLL or DLL, in which here you have the correlators. The outputs of them are the early, prompt, and late samples that I was referring before. And then we have some functions that we call discriminators that compute the error we are committing in that instant. And we reinject this error to a local numerical control oscillator that is applied to the input signal. So this closes the loop, and this is how a synchronization loop works here in order to track these satellite signals and know what are the difference in time of arrival in each of them. Then you need to demodulate the navigation message, which is the one that conveys information about the ephemeris parameters that describe the orbits, time parameters, clock corrections, the status of satellites. They also bring some ionospheric parameters that you can use for compensating the effect of the ionosphere in that precise moment, and the almanac, which is the information of other satellites in the same constellation. So you need to demodulate that signal and extract the information you want. Finally, from that information, you can build what is called the observables, which are the measurements from any GNSS receiver. The first one, we call it pseudo range, which is a measurement which is related to the physical distance from you to the satellite, but also affected by the difference between the clock offset of the satellite and your own receiver clock. This is why we call it pseudo range, because it's not exactly the geometrical range with this term, but it is affected by clock drift and by atmospheric effects like the ionosphere, troposphere, or measurement noises. Then we have a similar measurement, but not for the distance, but for the phase. This is based on, this computation is based on the delay. This one is based on the evolution of the carrier phase. And then we can have another similar measurement for the Doppler shift. These are the three observables we can get for one satellite. And we need this set of measurements. We need at least 4 sets of this, one for each satellite, in order to be able to compute the position. And this is what the PBT block does, actually. It collects all these observables and compute the position, the velocity, and the time of the user. And then it provides this information in different formats. For instance, if you want to plot your position in Geographic Information Systems or Air Browser or whatever, you can have KML, GPX, or GeoJSON formats. Then we have other formats for post-processing applications like RINEX files from observables and navigation, or maybe you want to integrate that with other systems. You have NMEA protocol for that, or RTCM, which is for real-time broadcasting of this kind of signals. Okay, so once we have the receiver, we want to test it. And we know that everything that it is not automatically tested will break someday, so have a good coverage of test of all the feature of software features is very important. We must include typical testing procedure for this integrated circuit-based GNSS receiver. Here I'm meaning the time to first fix, for instance, or the precision you get in 10 seconds of signal, whatever test you can do with regular GNSS receiver, you should be able to do that exactly the same with a software-defined one. But since this is software, we need to have a broader approach to testing, not only taking that as a regular receiver, but some things that are specific of software systems. And this is something that we need to be taken into account from the scratch, from the very beginning. You need to design for testability, and it's good to have this test-driven development in which you first write the test, and then you write the thing that implements what the test is checking. So this is quite good for the development. And for that, we use a library, which is also open source. It's released by Google. It's called the Google C++ testing framework. We have more than 2,000 tests for that, and everything is automated in a GitLab server. I will show that later. So beware of unit tests. They are very nice, but they are not the holy grail. So you always need system tests, and you need to be sure that everything is working right, apart from this unit test. So we have a development ecosystem, which is based on a web page. You have there a quick start guide for start working with the software, a description of this architecture. You have tutorial for doing specific things. You have documentation of the signal processing inside. The web page itself, it is in a GitHub repository, so you can see the source of the web page. You can contribute to it, wherever. Then we have the open source, which is a repository at GitHub. Here you have the pointer. we have a continuous integration system deployed at GitLab, which means every moment we do a small change in the code, this triggers a broad range of tests, compilation in different systems, wherever, in order to ensure that we have not broken anything. Okay? And the building process manager is CMake, which is also pretty standard. So the documentation is very important. This tweet expresses quite well a typical problem in software reason in the academia, in which, well, you can download the software, but sometimes you need to download the postdoc student that is the only guy that can make it work. So this is something that we wanted to avoid from the beginning. This is what we are putting quite effort on the documentation. So in the documentation, we have all the processing blocks and all the parameters. All this is documented in the website. As I said, we have tutorials, which are detailed instructions on how to build the software, how to do experiments. And we also have some tools for developers, such as automated code formatting. We are using code linters to detect bugs and these kind of things, even contribution guidelines. And we try to make contributors easy to work with us. Yeah. We have also a Git branching model in which we have two branches which are eternal with infinite lifetime, which is this master branch, which is where the last released software is. And then we have this next branch, which is where all development takes part. We usually work here, and once we have something that we think is ready, we can do another stable release. This is how we work. This use of Git is quite nice because it's very well connected to the signs of improvement. These people that talk about these plan, do, check, act cycles, which are pretty nice fit to the scientific method, in which first of all you plan, you create a branch from the current baseline, then you start to do work on that. Then you check that your work actually is correct, that you are not breaking anything. And if everything is nice, you inject this new feature, and it becomes the new baseline of the software. So working in these cycles, we can we can work at the same time in different aspects of the receiver, and even don't have a control of all of it. We have also a system of continuous integration that we have expanded to something that we call continuous reproducibility of experiments. That means that if there are a group of researchers that publish some research paper in which you have there some plots and some figures, it would be nice for to give the opportunity to everybody else to reproduce exactly the same experiment, and maybe with a different set of data, and see how it works. This would be very nice. This is what we are doing here. So once the code is in the upstream repository, there is an automatic system that builds this software in different versions of Linux operating systems in order to be sure that it can compile everywhere. Then we run a battery of tests just to be sure that everything is running smoothly. And then when we have that, we do something that is called software containerization, which is nothing more than bringing all this software in a Docker container. And you can move this which is a full stack of the software, from everything, the operating system and your software, everything in a single stack that can run anywhere. So we can move this container everywhere and run different kinds of experiments using one configuration and a GNSS dataset, or maybe the user wants to use another configuration and another dataset, wherever, and automatically they can run the experiment, get the validation, get the results, and compare the results with the original paper and see if they fit or not. So this is the automatic system that we have set up in order to let other people, without any kind of effort, just reproduce the experiment and see how they work. So at the building stage, we work with several Linux distributions and different versions, namely Arch Linux, CentOS, Debian, Fedora, OpenSUSE, Ubuntu, and we have also a cross-compilation kit for embedded devices. All of this is run every time we do a change in the repository. We use static code analysis tools. In this case, it's called CovarityScan, which offer free scanning for open source projects. Then we run all the units and system tests, and we do this software containerization and deployment in the Docker Hub. So this has clear benefits: the early detection of newly introduced bugs, the early detection of backward or even forward incompatibilities. When a new version of an operating system is released, we can quickly see if our software is running there or not, and we can be fast in correcting that. And also a fair assessment of new changes. If someone is claiming that his algorithm is much better than the rest, we can just plug it there and see how it works. With the same signals, everything is the same, so it allows you to do a fair assessment of algorithms. So let me show some possibilities of this technology that we have explored. The first one is a receiver in the cloud, not in your own computer, but in the cloud. This is where the virtualized GNSS receiver arises. As I said before, this virtualization consists on packing the full stack of software in a single unit. You can do that in several ways. The first one is a virtual machine, in which you just have everything there. This would be your virtual machine here, in which this is your application. In this case, would be GNSS DR. Then you have the libraries and binaries you need for running it. You have the guest operating system. And all this is run in a host operating system. And there is an hypervisor here that manages all the different virtual machines that can run in a single host machine. This is one approach. There's another one which is lighter, which is this software containerization, in which you have applications, you have the binaries, you have the container engine here, and the host operating system. So here you skip some parts of what a virtual machine packs. So this is lighter and maybe more efficient. You can put more containers in a single machine than virtual machine. So it's quite nice. So this is what we've done with our software. Put it in a Docker container. Actually, it's quite easy. You just have to define what is called a Docker file with instructions of what the packaging thing will have to do, and you get an image and a container, which essentially is your software receiver packed in a way that can be run anywhere in any computer, so you can put that in the cloud and it will be an actual receiver. So what we could do with that? This is something that come into our mind. Okay, let's try to do as people from mobile communications do this. You can put all your baseband engines in the cloud. That means that you can physically separate your antennas from your baseband engine. This is what we have done here, but since you need a quite large bandwidth for GNSS systems, the narrowest one is GPS L1, which is 2 megahertz, which is quite a lot. So you need a quite powerful communication network, in order to bring the signal from the antenna to a data center in which your software receiver is running. So we used an optical network, in which we place here an antenna. Then directly, well, there was an amplifier, but antenna, amplifier, and then we converted radio frequency into light. We injected that in a real optical network. And on the other side, we have this optical to electrical converter. We have here radio frequency again. Then we have a radio frequency front end, and then the samples can be injected into a data center. This could be a setup for static reference stations, because you need a connection to an optical network, so you cannot move. And if you want to do that wireless, well, maybe with 5G, there are some 5G modes that could allow you to do that, because you really need to send quite amount of information if you want to do continuous receiving of this signal. So this was the idea. And then we did an experiment to check if this actually worked. We have here one antenna, a couple of amplifiers, the electrical to optical transceiver. Here we have light. Then here we have an optical switch, 35 kilometers of optical fiber, then another optical switch. Then we converted light into radio frequency into bits, and we injected that into a computer. These are the picture of the experiments. These are the antennas that we have in the roof of our facilities. This is the electrical to optical converter, so the signal of the antenna arrives here. This is the modulator, and here you have the laser modulated by radio frequency. This is pretty cool. Then we used a real optical network. Here you have the coil with 35 kilometers of optical fiber. And then, just to place here an optical to electrical converter, a USRP, which is a typical front end, and the output of the front end just plugged onto a computer. We used for all these things open source. We manage all the optical network by software is called OpenStack. And the virtualization technologies, we tried both GNSS DR on a virtual box, which is a virtual machine, or a GNSS DR on a Docker container. We tried it both, and both worked well. We see that we can actually make a system deployment, so we can deploy this service in a real network in less than 20 seconds. So the creation of the virtual network took 12 seconds, and the light path setup of the optical network took 4 seconds, which is pretty fast. We also saw that the latency was very stable, and we could measure it, so this is really good. From our measurements, we got that the latency was 177 microseconds. Most of the part was the light propagation in this 35 kilometers of fiber. So the latency is pretty much controlled. And well, we actually worked, and it actually worked, and we could got position, velocity, and time fixes using live GPS and Galileo signals. And both of the virtualization mechanisms worked well there. So this is an approach we did, something that we can do with a software receiver, and it's something that we cannot do with a regular receiver. The second exploration we did is, okay, this works in a computer, let's see if we can make it work in a small device. So if you want to use the software outside of your office or your lab, a personal computer is not the best form factor, because they are big, and even if you have a good computer, if you want to work with a complex configuration, that means you want to work with GPS, with Galileo, with GLONASS in different bands, this is a lot of signal processing load. So even with a modern computer, it's tough to reach real time. So this is why we resorted to FPGA offloading. So we moved into an FPGA, the most consuming parts of the processing, which actually are FFTs and correlations. We need to change a little bit the structure. This is the proposed receiver architecture, in which we have an integrated circuit, which is a radio frequency front end, and then inside of a Xilinx Think processor, we got here the processing part in the FPGA, and the rest is running in an ARM device. So this is the architecture for the embedded system. Little modifications of the flow graph, because if you see here, the samples enter the FPGA before the ARM, so you cannot manage this part with GNU Radio. So we need to invent something in which the tracking blocks and the acquisition blocks becomes sources, and in this way we can reuse the software from tracking and acquisition. All the rest can be reused in just the same way. And we just have to program the modules inside the FPGA for FFT and correlations. This is the picture of the whole thing. This is like a credit card size, in which here you have the radio frequency front end, here you have the processor. So in a very, very small device, you have everything. You can plug the antenna here, and you can get your position here in an Ethernet cable. So it's pretty small. We also did some 3D printing in order to have a safe manipulation in and outside the lab of the receiver. And then we have also developed a software development kit created with Open Embedded, which provides a cross-compilation environment for embedded systems. If you need to compile the software in an ARM device, it can take a couple of days. If you use cross-compilation in a powerful computing, it takes 10 minutes. So it is a really good thing to have this software development kit for embedded devices. We can do some receiver in the loop testing setups, in which we have a receiver here. We can use a professional signal simulator, and then we can compare, which is the results of the processing of our receiver, what would be the reference provided by the GNSS simulator, and have some quantitative measurements of the quality of our processing. So the third case we are exploring is to put this software in the space and see if it can work with higher dynamics. So space is really an excellent scenario for SDRs, because it requires features of the GNSS receiver that are not standard, and probably they are not in commercial integrated circuits. SDR also offers reprogrammability on self-healing, which is also important in space technology. For instance, you can upload algorithms to the spacecraft which were not invented at the time of the launching, so this is quite nice. Or the ability to recover from a single event by remotely rewriting damaged functionalities and reducing the need of onboard redundancy, which is also good. There is an interest on spaceborne GNSS receivers. Here you have a short list of applications, which is much longer, but just to mention applications of precise orbit determination, autonomous orbit control, maneuver planning and managing, spacecraft formation flagging, or for instance this thing here, which is called radio occultation, in which if you have your receiver here in orbit and you have a GPS receiver here, you can use this diffraction in order to have a very nice profile of the ionosphere here. This is called radio occultation. Or GNSS reflectometry, which is also a very interesting application. There are some challenges there in space, apart from radiation and so on. The first thing is that you need to reduce the power consumption. the Doppler rate you can expect is much higher wider than on Earth. On Earth, you can expect 5 kilohertz at maximum of Doppler, and in space you have 60 in a LEO orbit, a low Earth orbit. Of course, increased dynamic range and the signal received power. If you are above the GPS satellites that are broadcasting to the Earth, you are not seeing them. You have to see the ones that at the other side of the Earth, which reaches you with much less power. So this is the kind of problems you have in space. And actually, we make it work. We need to make modifications to those tracking loops I mentioned before in order to take into account for the Doppler, not the Doppler shift, but the Doppler rate. And here you have the outputs of the discriminators, the correlators. Here you have the recovered bits. So with all this information, this is for GPS L1. These are results for GPS L1. These are results for Galileo E1. And here you have the results we got from 5 minutes of signals captured in space. So it actually works. So to finalize, just brief conclusions here. We have a star alignment in the sense that the open design trend of hardware and software, this is very nice. The software-defined everything trend, not only software-defined radio, but also software-defined networks. The rise of GNSS, in 20 years, we have passed from 24 satellites and 1 open service signal to more than 100 satellites, 18 different open service signals, 4 different systems. All this in 20 years. For programming engineering, for software, 20 years is a glacial era, but for space technology is quite short. So we have right now here, we have the ability of affordable components of the shelf, commercial, for radio frequency front ends. We have the ability, the availability of free and open source software tools, so we can start play today. And this is an enabling technology for new uses of GNSS signals. It has application on very disparate fields, analysis of space weather, precision agriculture. You can provide precision, levels of precision as a service, which is quite new. Distributed position ledgers, or just for education. You can do a lot of things with this. And GNSSDR is just an example, scratching the surface of all the software-defined radio concept can be applied to GNSSDR. So thank you very much for your attention. Here you have pointers to the website. There is an open discussion in the website of how a good GNSS receiver defined by software should be in terms of accuracy, availability, and all the list of features we have here. And all kinds of contributions, of course, are welcome. So thank you very much for your attention.
So thank you very much. Are there questions?
Yes, around slide 45 you mentioned actually extending a GPS signal over a fiber of 35 kilometers, something like that.
Mm-hmm.
Oh no, it was even earlier, I think, or later. Yeah. Yeah, you extended. Would you, if you calculate the position or derive time, were you able to also calculate the common bias by all the factors which are in there?
Sure. There are a lot of things you can do with that. It's actually a thing to play with, and every time we do experiments, they come up with different ideas to do with that. Yes, it's very nice. So, for instance, here we have a measure of the latency from the antenna to the data center. So we saw that this is very stable over a day of real usage of the optical network. So yes, with different, you could have different receivers, you could have different biases, and and just combine this information. So yes, very nice. Thank you.
I think. Just talk.
Again? Does it work?
I don't think so. No.
Okay. Just the obvious question which I missed in your talk. When this is an SDR GNSS decoder software, what kind of computational resources in common computational units do you need? So if you want to run this instead of some FPGA board, run it on a Pentium, or if you're cloud, how many compute instances do you need to purchase from Amazon?
If you want to run a receiver, it works. Yeah. If you want to work with a receiver just with one system and one band, any regular computer will work. Even a Raspberry Pi can do the work for you. But if you want different bands with different systems, wherever, you need more computational power. For basic positioning, we do that in a Raspberry Pi. Mm-hmm.
Okay.
Okay, if you could please go back to the slide around 50, I think. No, earlier than the one where you're showing the results from your experiment with optical fiber transport. Yeah, that one. No, one forward, I think. No, one back now. Yeah. One back, please. Yes. No, sorry, this is also another one. The one where you mentioned the actual propagation time through the fiber.
Ah, yeah.
Yeah.
Mm-hmm.
So those numbers look a little bit off to me in the sense that you are calculating the speed of light through the fiber, whereas in fiber, light actually only goes at a speed of about 2/3 of the speed of light. So actually, all those 177 microseconds are actually your propagation time.
Yeah, you're right.
Okay.
You're right. That's true.
And
The thing that I wanted to convey in this slide is that this measurement is quite stable over time. This is important, because if the latency is moving, you have a problem.
Yeah, maybe we should take that one offline. The other quick question I had is the software able to do dispersion measurement by looking at, say, L1 and L5?
Yes.
That's already implemented?
Yeah.
Awesome.
Yeah.
Thank you.
Mm-hmm.
Okay, any more questions? No more questions? So then, Carlos, thank you very, very much.